Hello, welcome to the presentation of my poster for the 14th International Conference on Surface Materials and Vacuum 2021. I'm Jorge Alberto Polito Lucas, and I go to tell you about my research work entitled Optical Response of Pure Metal and Metal Nitride Fields by Numerical Simulation. In this work, we report the reflectance of dim fields obtained by numerical simulation using discrete dipole approximation implemented in the DSCAD code. These calculations were performed for films of niobium, titanium, and their respective nitrides, niobium and titanium nitride. Discrete dipole approximation consists of discretizing a target into electrical dipoles. This target can be from a macroscopic object to one of the order of nanometers. A first approximation is to consider a target unit cell TUC, which will be repeated in space by means of periodic boundary conditions. DDSCAD allows to obtain the reflection and transmission coefficient through the elements S11 and S12 of the Mueller matrix. Expression 1 to 4 show the analytical form of the reflection and transmission coefficients, parallel and perpendicular with respect to the target surface. For a better study of the reflection and transmission spectra, it is necessary to introduce the dielectric fusion. It must be considered that the dielectric fusion of bulk material is composed of the contribution of intraband electrons, those that are free electrons or in the valence shell of the atoms, and interband electrons, those electrons in deep shells and that are bound to the nucleus of the atom. The dielectric fusion of the intraband electron is studied on the basis of the truth model for metals, but the analytical form of the interband dielectric fusion is not known to use. It can be accessed by clearing it from equation 5. Expression 6 is the dielectric fusion obtained from the truth model, while with expression 7 it is possible to model the dielectric fusion of the interband electrons. For the experimental part, niobium dim fields were deposited by DC magnetron sputtering at different outward working pressures. Thickness and ruggedness were estimated by AFM measurements. The ruggedness found in the samples was less than 1 nanometer, so they can be considered as a smooth film. A convergence study was carried out to determine the appropriate number of dipoles in the TUC. It can be seen that for all 4 materials a TUC with 50 dipoles is necessary to ensure convergence in the numerical calculations. In the case of niobium and titanium, peaks below 350 nanometers are observed. These peaks are mainly due to contribution from the interband electrons. This can be verified by studying the dielectric fusion of niobium, where a feed of the dielectric fusion of the interband electrons to the dielectric fusion of the material below 400 nanometers is observed, and below 500 nanometers for titanium. Only for the case of niobium was comparison with experimental results. In this case, numerical calculation will rely for 100 nanometers thick film as a function of the incident angle, 30, 45, and 60 degrees. In addition, 2 types of linear polarization were used, S-type and P-type. For the samples S1, panel C, and S3, panel E, a trend found with the numerical calculation is observed. It else, the intensity or RS spectra increases with the incident angle. Conversely, RP spectra decreases as the incident angle increases. As conclusion, we can mention that we have obtained reflectance spectra for 4 materials: niobium, titanium, niobium nitride, and titanium nitride by means of DDA, ensuring convergence in the numerical calculation from the use of 50 dipole TUC. Of the materials studied, niobium presents a higher reflectance in the UV range, within which optical bands were observed. These bands correspond mainly to contribution from interband electrons. Finally, as the angle of incidence increases, the intensity of the reflectance spectra with S-type polarization increases. With P-type polarization, it decreases. However, an experimental study in the UV range is still needed to verify the presence of the bands obtained by numerical calculations. Finally, I would like to thank the support of BFWAP and CONACYT for the realization of this work. I would also like to thank Dr. Francisco Javier Flores Ruiz for his support in the AFM measurements. Bye bye.